Thank you very, very much indeed for joining us on this 50th occasion, which I guess is 5 years of Wantage Café Scientifique, which is fantastic. And I must say, I think we've been spoiled with some a variety of wonderful talks, wonderful speakers, and I'd like to do a shout out, a big thank you to Faith for all the time and heavy lifting that she does to organize the program. A really fantastic job. And ironically, we're just being joined by Mim. So Mim, I've just done a shout out for the 50th talk, many of which you organized. So thank you very much for all you've done for Café Scientifique too. We have, again, another fantastic speaker, very distinguished scientist, Peter Allan, who, Peter, I think I'm right in saying you took your PhD in Manchester.
That's
but
right.
You did research in astronomy in the Netherlands, in America, and you have been associated with RAL Space at Rutherford Abbott Lab for 30 years now.
Yes,
so
30 years this year.
There ain't many people better qualified to give a talk like this one. You are Stardust. Thank you to everybody for all their support for Café Scientifique over those 50 talks. But the one you want to hear is Peter. Hand over to Peter.
Right, I shall attempt to share my screen. That's the one that we want. Right, John, can you see the screen saying "We are Stardust" and a picture of Orion?
Yes, sir.
Okay, excellent. Right, good evening, everyone. The title of my talk tonight is "We are Stardust," and as I'm sure you read in the blurb, I will aim to show you how we know that this is literally true. All of the elements that make up us and everything that we touch and feel around us have come out of stars, except for hydrogen. Hydrogen was there in the first place. So the phrase "We are Stardust," as far as I can track it down, does originate with Joni Mitchell and the chorus of her song "Woodstock." I'm sure you've heard of this before. I did wonder if it was from Carl Sagan. It's the sort of thing that he might have said, but his phrase was actually "We are star stuff." I think Stardust just has a nicer ring to it, so I'm going with that for the title. So let me just give you an outline of what I'll be talking about this evening. So I'll talk about what are we made of, hence the pictures of humans at the top. What are stars made of? That picture is supposed to show the interior of the sun. Where do all the chemical elements come from? And how, in the heavens, do they end up here on the Earth and in us? So let's just start at the beginning. So what is stuff made of? I'll be using this word stuff a bit during my talk, and I just don't want to get too specific about things. I'm just talking about things that we can touch and feel. A bit of wood, the air around us, water, it's all stuff. So everything physical is made up from atoms. So an atom, it's the smallest unit of matter that forms a chemical element. There's many different types of atoms. There's 100 different chemical elements, and they are really small. Those two circles are meant to represent just two different sorts of chemical elements, different atoms, and the size scale there shows that the red one is approximately 1/10,000,000th of a millimeter in size. That is pretty small. And so that's why we never see atoms. They're just really small. And there's a lot of them in essentially anything that you can touch. There are many different chemical elements. Some of them have been known for thousands of years. I've got part of a table here. I'm not going to go through it in great detail, but ones that have been known for thousands of years are mostly metals, so things like copper, gold, silver, iron. And we know those because you can really just go out and dig them up out of the ground, whereas some things are rather harder to isolate as a chemical element. Working forwards in terms of when things were discovered, the 18th century was really a golden age for discovering new elements. So this is when the science of chemistry was really taking off, and you could do chemical reactions. You could take things that were one sort of element, merge them with different sorts of elements, and make a new sort of stuff. You're not changing the elements that are in there, but you are making a new sort of stuff. The reason I've highlighted helium on this table is that helium was actually discovered in the sun before it was discovered on the Earth, which is quite unusual, and I'll be showing you how that might happen a bit later on in the talk. So just to give an idea of what the structure of an atom looks like, this is the classical way of representing one atom. So on the left, we've got a hydrogen atom, which has got a nucleus consisting of one proton and an electron going around it. This is horribly inaccurate in two ways. One is that the size of the nucleus, if the size of the atom was drawn correctly, is about 1,000th of a pixel on your screen, not that big, nice red circle with a plus sign in it. And also, it really rather gives you the idea that an atom is rather like the solar system. You've got the sun in the middle and the electron orbiting around in the way that a planet orbits around the solar system. This is horribly wrong, but the reason that this representation exists is that it's really hard to come up with anything better. A better representation is to think of the electrons as bees buzzing around. So we've got a connection to the last talk that we had. So instead of just circling around nicely, the electron is a bit more like, in this case, one bee, just buzzing around the nucleus, going here, there, and everywhere. Even that's not accurate, but it's slightly more realistic than the idea of something orbiting around. As we move to other heavier elements, the next one is helium, where the nucleus consists of 2 protons and 2 neutrons. We've got a new particle here, a neutron in the nucleus. And again, it's really, really tiny, and we've got 2 electrons going around it. And as you move through the different chemical elements, then you're adding a proton each time to get a new chemical element. It's the number of protons that distinguish one element from another. And by and large, in the lower mass atoms, then you've got the same number of neutrons as protons. That's not exactly true, but it's more or less true. And so we've got over 100 chemical elements these days. I'm sure you recognize this as the periodic table. When chemistry was really taking off back in the 18th century and all these different chemical elements were being discovered, then people were trying to put them into some sort, first of all, into some sort of order, and then noticing that different chemical elements had somewhat different properties. And that's where this periodic table, developed by John Dalton, came in. So as you go down one column, so just looking at the left-hand column, where it says period going down, then we've got things which have got rather similar chemical properties. So lithium, sodium, potassium, and so on have got rather similar chemical properties. Over on the right-hand side, we've got helium, neon, argon, krypton, and so on. These are the inert gases, the noble gases, which just don't interact with anything. So again, similar chemical properties. For fans of pointless, you will be pleased to notice that we've got tennessine and oganesson down at the bottom right-hand corner. And those are, it was actually 2 of the last 4 chemical elements to be made. The really high mass chemical elements can only be made in the laboratory. They just don't exist in nature. So let's go back to what is stuff made of. Most stuff is actually made from compounds where you've got two or more elements combined together. So it's not just a single element. So for example, water is made from hydrogen and oxygen, and there's a little cartoon showing how that might be done in the bottom right hand corner. So one molecule of water consists of two atoms of hydrogen bound to one atom of oxygen. And because you can put things together in many, many different ways, there are many more than 100 different types of stuff. So the first question was, what are we made of? So humans, made of skin, bones, blood, muscle, brain, fat. Well, yes, but the question is, what chemical elements are we made of here? And in terms of the chemical elements, then a lot of us is made of oxygen, and then we've got carbon, hydrogen, nitrogen, calcium, phosphorus. Those are all things that are more than 1% for each of the elements. We've then got potassium, sulfur, sodium, chlorine, magnesium. That's taking us down to where these things are only 0.1% of what makes us up. And you might think that, well, there's many other elements, but if everything else adds up to 1% of what makes up a human, then surely those other things are not really that important. And that's just not true. So I've got here a periodic table that shows how much of a human is made up of each element. So if we just take an example of salt, sodium chloride over on the left, we've got sodium, 1.5 parts in 1,000, chlorine, 1.5 parts in 1,000. So only a few parts in 1,000 of a human is made up of salt. And yet, if we don't have salt in our bodies, then we get ill very quickly. If we look at iron, 60 parts per million, is that really important? Well, iron is an important part of hemoglobin in the blood. No hemoglobin and blood doesn't work. So again, that's really important for how a human works. And nearly all of the things which are coloured in, showing that they do occur in the human body, are important for how a human functions. So we're really quite complex entities, chemically speaking. So let me just have a summary of where we got to so far. We've got over 100 different elements, and everything physical, including us, is made up of these elements. So, big question, where did all these elements come from? And obviously you know the answer I'm working towards. They were made in stars. Not absolutely everything, but nearly everything. There's various possibilities. Firstly, the elements could just be there. They're just there, or the elements were created somehow at some point in the past, or the elements are still being created somehow now. If we just put that into slightly more scientific language, then the elements just being there, well, we would say, well, they were created in the Big Bang. Right at the beginning of the universe, the elements came to be. Or if they were created somehow in the past, then they were created sometime in the early universe, not specifying when at the moment, but sometime in the early universe. Or maybe the process of creation is going on now. We'll see that all of these things actually do occur, but most of the elements are being created right now and throughout some of the recent history of the universe. So, what are stars made of? If we're going to say that things come out of stars, then we need to know what stars are actually made of. Now, how on Earth, or how in the heavens, can we know that? Stars are billions of kilometers away from us, and those are the nearby stars. That's true, but the light from the stars reaches us. Here's a nice picture of the constellation of Orion. Top left-hand corner, we've got the rather orangey red star, known either as Betelgeuse or Betelgeuse. That was in the news a few months ago because the star actually got considerably dimmer. And this is a star that we know is towards the end of its lifetime. And so we are expecting it to do exciting things. One day it's going to blow up, but that might not be for hundreds of thousands of years, or it might be tomorrow. So in order to find out what stars are made of, we can study the light that comes from us using a spectroscope. And we do this in the laboratory as well. If we want to study what things around us are made of, then you can heat them up. You can look at the light through a prism or some other device that splits up the light into different colours. Now, this works because atoms emit and absorb light of very specific colours or wavelengths. So the diagram on the right is meant to show different energy levels in an atom. It's hydrogen, so it's nice and simple. And the point here is that an atom can have different energy levels. You can't put an atom into just any old energy. It's very specific ones. So normally a hydrogen atom will just be sat at the lowest energy level. It's relaxed. Nothing's caused it to go up to a higher energy level. But if a photon of light comes along of just the right energy, it can be absorbed and the atom can be excited to a higher level. And this does happen. But you can't put it somewhere in the gaps between the rungs on that ladder. Atoms just don't work that way. You've got to have it on one of those specific energy levels. And we can look at starlight in the same way as we can look at heating up objects in the laboratory. And here we've got a picture of what happens when you look at the sun through a spectroscope. You see the colours of the rainbow, not surprisingly. A spectroscope works in basically the same way as a rainbow does. But you see all of these dark lines across the different colours. And each dark line is caused by a particular element, or particularly a pair of energy levels in a particular element, absorbing the light that's coming out of the sun. And we can identify every single line and relate it to a particular energy level in particular atoms. And that lets us study what the chemical composition of, in this case, the sun is. And if we can do it for the sun, we can do it for other stars as well. And so through these means, then we can actually determine the chemical composition of stars, certainly within our galaxy and beyond for bright stars. So we can measure not just the presence, but the abundance of the elements in the atmosphere of stars. So we know what they're made of, and we know how much of each element makes up stars. And we can do the same for clouds of gas around stars, a picture of a cloud of gas there on the right, and also the gas that forms the medium between the stars. The fainter the thing that you look at, the harder it gets, but we've got big telescopes these days. We can study these things in quite exquisite detail. So by doing this, then we can actually measure the abundance of all of the elements out there in the universe. And that's what this picture is showing. We've got the atomic number along the bottom, which essentially is just telling you which element we've got. We've got, reading from left to right, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, and so on, up to uranium. And it's important to notice that the vertical scale is a logarithmic one, which means that every time the number increases by 1, the abundance has gone up by 10. And so although carbon may not look to be so far down the scale compared with hydrogen, then it's actually less than 1,000th of the abundance of hydrogen. And so hydrogen and helium are relatively common, and everything else in the universe is relatively scarce. If you draw that on a pie chart and put the actual numbers on, then 75% of the universe consists of hydrogen, 25% consists of helium, and everything else is a very small fraction. So carbon, nitrogen, and oxygen, things that were relatively high up on this graph, are only about 1 part in 10,000. And these proportions are done by the mass of the atom. It's different if you count the number of atoms, but conventionally we express it as a fraction by mass. So I'll just say a little bit about chemical reactions, because I'm going to compare them with nuclear reactions in a minute. I've just taken a particularly simple chemical reaction here. We've taken some sodium. Sodium's a metal. You can get a chunk of it. You can put it in water, and this is what happens. So please don't try it at home. You get a lot of fizzing and things spluttering out. But chemically, what's happening is that for every 2 atoms of sodium in the chunk of metal that you've thrown in the water, reacts with 2 molecules of water to create 2 molecules of sodium hydroxide and 1 molecule of hydrogen gas. And the point here is that the number of atoms of each element doesn't change in this reaction. And in terms of counting the number of atoms, what comes out is what went in. And chemistry is really all about how the electrons in atoms change their arrangement when you put different elements together. And we see this in action every day. Chemistry is going on all around us. Cooking, burning, breathing, these are all different chemical reactions. To contrast that with nuclear reactions, so when we're talking about nuclear reactions, we're no longer talking about the atom as a whole, but the very small nucleus at the center of the atom. So just to pick on one that is particularly important for power generation, if you've got a nucleus of uranium-235, so uranium has got 92 protons in it, and it will have, how much is it? Well, 235 minus 92 neutrons in it. And if you hit that with a neutron, which is flying around in the space between the atoms for whatever reason, it's absorbed and you get uranium-236. It's still uranium, but it's got 1 more neutron in the nucleus. That 1 more neutron makes the nucleus particularly unstable, and so it actually splits into 2 different elements. You've got krypton and you've got barium that are coming out of this nuclear reaction, and 3 more neutrons and lots of energy, which is why we use this for generating power from nuclear sources. And the fact that 3 neutrons comes out means that these 3 neutrons on the right can then hit 3 more nuclei of uranium and generate even more energy. So you do have to be careful you don't get a runaway reaction here. The structure of the nucleus is changing when you're having these nuclear reactions, and in particular we're creating new chemical elements that we didn't have when we started. So if we can change one element into another, then we can actually create elements. That's an important part of the story of where the elements came from. So, to summarize here, there are about 100 different types of elements. Stuff is often made by making compounds of these elements. Chemistry is about how the electrons in different atoms interact. Nuclear physics is about how the constituents of the nucleus interact. The electrons are essentially irrelevant at this point. So, moving on, what looks like a completely different subject, but it's going to be crucial in a moment. What powers the stars? This was actually a big mystery at the end of the 19th century. Astronomy was a well-respected science. We've been observing stars for centuries, and we'd made enough measurements to know how much power a star puts out, and we had a pretty good idea of how long a star lasted, what its lifetime was. Trouble was that any known source of fuel, such as coal, could not power a star for its known lifetime. And it was only when nuclear reactions and the possibility of nuclear power was realized that scientists realized that it's nuclear reactions that power the stars. So the sun is actually a nuclear power plant. It's all driven by the one equation in physics that everyone knows, E equals mc squared. And the way to read this in this context is that if we destroy an amount of mass m, then we create an amount of energy E. So by destroying mass, we actually create energy. Now, if you remember your chemistry from school, you were probably told that we cannot create or destroy mass. That is perfectly true in chemical reactions, but in nuclear reactions, we do create or destroy mass, and hence we absorb or emit energy, and a lot of it. So, what actually powers the sun? The nuclear reactions that are involved, given that the sun is, that the universe is mostly hydrogen, it's not surprising that hydrogen is the main constituent here. So I've got a diagram which is going to grow as I go through the next 3 slides. What we've got is we've got hydrogen at very high temperatures, which they are just protons, hydrogen nuclei. 2 of them can hit each other at very high speeds. That's what the spark thing in the middle is meant to indicate. And what happens is that you create a deuterium nucleus, otherwise known as hydrogen 2. You also get an electron, sorry, a positron coming out. So this is antimatter, and something called a neutrino. That's something that's needed to balance the energy in the reactions that are going on here. So we've taken hydrogen, but it's still hydrogen. It's a different form of hydrogen, but it's still just hydrogen. Then that deuterium is hit by another hydrogen nucleus. Again, we've got another spark in the middle, and this creates helium-3. So it's helium because we've got 2 protons there and 1 neutron, so the mass number is 3. And the gamma ray comes out as well. This happens nearby, so the bottom part of this picture is just the same as the top. So we've now got 2 helium nuclei, helium-3 nuclei, which hit each other. And what you get out of that is helium-4 and 2 protons. So it's a chain of 3 different types of reactions going on here in the middle of the sun. So the result of all of these reactions is that what went in was 4 protons, also known as hydrogen nuclei. And what came out was a helium-4 nucleus, 2 positrons, 2 neutrinos, and 2 gamma rays. If you count up the protons, you'll say, hang on, there were 6 protons going in. Well, yes, but 2 of them just come out again at the other side. So the net result is 4 protons converted into 1 helium-4 nucleus. And in terms of energy generation, the mass of what comes out is 0.7% less than what went in. So mass is being destroyed in the center of the sun, and this is what creates the energy that makes the sun shine. So, have we got any evidence that this is actually what's happening? Well, the temperatures at the center of the sun are those needed for these reactions to generate an appreciable amount of energy. You've got to hit the protons together for that first reaction at very high speed, very great energy, and the temperature in the middle of the sun is about 14 million degrees Kelvin or centigrade. At that level, there's no difference between them. Well, that's all very well. This is all theory. You can't see what's going on in the middle of the sun, can you? Well, these days we can. I'll just flip back a bit. These neutrinos are particles which interact very, very weakly with anything. The ones coming from the sun towards the earth, most of them will just fly straight through the earth and out the other side. But if you build big enough detectors, you can catch a few of them. And so we build huge tanks. There's a person that you can get the scale of these things, fill them with water, and the neutrinos will hit the nucleus of water very occasionally, cause a flash of light, which are being picked up by these photocells around them. And so we can measure the rate of neutrino production in the center of the sun. So we are actually observing what's going on directly in the center of the sun. So that's what's going on in our sun. What about other stars? Well, stars that are similar to the sun have very similar reactions. It's called the PP1 chain. That's just the name that's given to it. There are stars with that are more massive than the sun, so they have higher temperatures. And there are other reactions. I won't go into the details. It's called the PP2 chain, PP3 chain, CNO cycle. But all of these have the net effect of converting 4 protons into a helium-4 nucleus. So again, we're generating energy and we are creating helium from hydrogen. So we are creating helium. So we've managed to create one element, helium, from hydrogen. You'll be pleased to know that I'm not going to go into every element in detail, or we'd be here till the weekend. We now need to look at what happens for the evolution of a star. For a star like the sun, it will burn hydrogen into helium for about 10 billion years. The sun's roughly 5 billion years old, so the sun is in its middle age. It's a nice calm star. It sits there, apart from outbursts from the surface. In terms of energy generation, it's just nicely generating energy at a very regular rate. But after 10 billion years, in the case of the sun, all of the hydrogen in the center of the sun will be used up. And so there's nothing there that's generating the heat. And so the pressure that keeps the sun up. And so the core of the sun will collapse, which squashes the gas, and that actually heats it up to even higher temperatures. And that allows the helium, which has been generated there, to burn into carbon and oxygen. And eventually, all of the helium in the core is used up, and so the core collapses again, raising it to even higher temperatures, allowing the carbon and the oxygen to burn into neon, sodium, magnesium, sulfur, and silicon. And this continues for a further step, allowing the elements I just mentioned to burn into calcium, chromium, iron, nickel, and copper. Now then, you might think, well, okay, does this just continue on and on? Well, the answer is no. Each of those steps, which was getting a bit more convoluted than the last one, generates less energy and lasts for a shorter time. And in particular, when you got to the last step where iron was generated, then that's the nucleus that is the most tightly bound, and you can't generate energy by adding things onto iron. The process that we've been going through so far is essentially taking a light element, ultimately hitting it with protons to generate a heavier element, and generating energy as a result. This process stops when you get up to iron, because if you did hit a proton into iron, which of course you can do, then it requires energy to generate the next element up. And so this isn't just going to occur naturally, and so the process stops. So the processes that I've gone through so far can generate elements up to element 29, copper. So we've still got a long way to go to get up to 100. So let me just pause to fill in a few details there. I talked about some of the elements. I listed some of the elements from element number 2, helium, up to 29, copper. The ones that I didn't mention are made via essentially the same processes, but with some additional reactions. You might be capturing a neutron or ejecting a neutron or capturing an electron or a positron in the nucleus to generate a different element. So we can generate lots of different elements this way. So we know the processes that are going on. It's standard nuclear physics. But an important question is, do these processes explain the observed abundances of each element that we actually see out there in the universe? And back in the 1950s, this heroic team put it all together. The people here are Margaret Burbidge, Geoffrey Burbidge, Willie Fowler, and Fred Hoyle. And they wrote one of the most referenced papers, certainly the most important papers ever in astrophysics, the synthesis of the elements in stars. What they did was to take all the work that was known at the time about the nuclear processes which could create elements in stars, and the abundances that we actually see out there in the universe, and asked the question, can we explain the abundances from the known stars that we see and from the known nuclear reactions? And the answer is yes, you can do everything except for helium. All of the elements apart from helium you can generate in stars. Now, I've been saying that helium is made in stars. Yes, it is, but stars only actually make a few % of helium. And you'll remember that the universe is 25% helium. So we can't explain that large amount of helium just by making it in stars. Fred Hoyle was hoping that the answer would be yes, it is all made in stars. But that's not the case. We need another place to make the helium. And the place where most of the helium is made is in the early universe. So I'm going to rewind right to the very beginning of the universe now. We have the Big Bang, which is unimaginably hot, where even protons didn't exist. You've just got things that are bashing into each other at incredibly high energy. So lots of reactions are going on. And then after fractions of a second, then the universe cools to a mere few trillion degrees Kelvin. At this stage, protons and neutrons can actually exist. And so we can have the sort of nuclear reactions that we can easily do in the laboratory when we talk about nuclear physics. By the time the universe has cooled down to a few billion degrees K, then now you can make helium and it could survive. So it's not being hit by something which is just going to destroy it. And in fact, most of the helium that's in the universe was made shortly after the Big Bang. There's a well-known book by Steven Weinberg called The First 3 Minutes, and it describes how helium is made as the universe expands and cools down for just the first 3 minutes of the existence of the universe. Now, all this actually requires is standard laboratory nuclear physics and an expanding hot universe. So it's hot and it cools down as it expands. So we can do the calculations, but again, are they right? Well, the graph on the right is meant to show if you've got different densities of matter, and it's just being measured relative to the number of photons, light, you've got around, and the elemental abundances. And you can see that as you increase the density of matter, then you create more helium-4. The deuterium actually drops off, Helium-3 goes through a peak and then falls off. And you make a tiny amount of lithium-7, which rises up, falls down, and then rises up again. And what you can do is you can compare the actual observed abundances with data from the Wilkinson Microwave Anisotropy Probe. It's a spacecraft that was launched, I think it's about 15 years ago now, possibly a bit longer. And the measurements fit exactly right. So this gives us confidence that this idea of creating helium in the early universe is correct. Now, you'll recall that I've still only got up to copper when I was talking about things before. We're talking about things towards the end of a star's life, and stars don't live forever. At the end of their lives, then massive stars, they've got winds that are blowing materials off their surfaces. You have outbursts, which are novae, or even the whole star explodes in a supernova explosion. And that ejects much of the contents of the star out into space. And so all of the elements that were created in the center get blown out into space. This is important, otherwise it's all very well creating them in a star, but we need to get them out. And also, a supernova explosion provides a lot of energy, and these can create many heavy elements. More recently, we observed, using a gravitational wave observatory, we saw two neutron stars that were merging into one. That created a huge explosion, which we saw using, I think it was about 70 different optical telescopes around the world. They were triggered by the detection of the gravitational waves. And everyone knew that this was really important. If we saw something, we should observe it in as much detail as we could. And a lot of telescope time was expended on that. And one thing we saw was gold being made in this merger of two neutron stars. So that was a very nice result that we got out of that. So what is shot out from these stellar explosions, these form clouds of gas and dust in the interstellar medium, the space between the stars. And we've observed such things for hundreds of years. The picture that I've got here is a picture of something called the Crab Nebula, which is the remnant of a supernova explosion. That's a picture taken using the Hubble Observatory. And in fact, because Hubble has got such fine detailed pictures, over the years we've been able to see that that cloud of gas is actually expanding. That wasn't possible with measurements from the ground. We needed Hubble to be able to see that that was happening. So let's summarize how elements are created. Hydrogen is made in the Big Bang as what we call the quark soup plasma cools enough to allow protons to form. Protons are the most basic elements of all. Most of the helium is made in the first 3 minutes of the universe as it cools down enough to allow complex nuclei to form. As I said, you get a small amount of lithium made there too. Beryllium and boron, I skated over those earlier on, but those are actually made by cosmic ray fission processes. You get a little helium and all the other elements up to plutonium made inside stars. There's an exception for the elements 43 and 61, technetium and promethium. And the reason that those, they will be made inside stars, but they're actually unstable. There is no stable isotope of technetium and promethium. So from a chemical point of view, they're gaps in the periodic table. Anything that's heavier than plutonium, you can only make in the laboratory. And that's simply because such elements just don't live for very long. They're fractions of a second. And so, yes, you can make them, but then they don't stick around very long. So redrawing the periodic table again, then I've got things coloured in here as to what processes created the element. So hydrogen is nice and simple. It was created in the Big Bang. Helium, it was created, well, 3 minutes after the Big Bang. You might say that was the Big Bang as well. And a little bit of other processes, the things I mentioned before. And as you work your way through this table, you find that the heavier elements were created inside stars, but the exploding stars. The relatively new bit is there's a lot of purple here, which is merging neutron stars. This was something that had been discussed for quite a long time, but it really wasn't experimentally verified until we saw this merging neutron stars just 3 years ago. And then the very heaviest ones are only made in the laboratory. So, I've told you how elements are made, but how do they end up in us? So, we've got clouds of gas and dust out in the interstellar medium that were created when stars exploded. These then collapse to form new stars. There's a picture of the Orion Nebula, which is a region where stars are forming. These things collapse to form stars, and they have planets going around them. At least one planet has developed life, some of which is called Homo sapiens, and I can hear you all going, ah, and that's why we are Stardust. Thank you. I think I need to stop sharing at this point.
Peter, that was amazing. Thank you very, very, very much indeed.
You're welcome. I suspect there's 2 questions.
If I said it was stellar, did I get away with that? Yeah, I should have said sooner, if anybody wants to post a question via the chat line, I'm hoping Faith will rescue me and pick up the questions to take us forward. I have to say, Peter, one thing in all this made me, left me with a kind of uncomfortable memory though. I didn't get on with my dad, but he was my chemistry teacher. So I learned the periodic table at his hands. So you've taken me down a bit of memory lane there. You also said something which I've never heard before, and I think points possibly to the biggest marketing failure of all time, that the nuclear industry didn't pick up your phrase that the sun was a nuclear power plant. If only they had done that, I think many, many millions would have been saved somewhere along the way. But that's a kind of a digression. Faith, are you on the call?
Sorry, yes, I've had a problem with my computer actually. I'm now Damien Culshaw, not Faith Culshaw.
I can wing it for a
yes.
bit longer if you want.
It meant I'm afraid I missed the second half of the talk, but anyway.
Okay, well, I can see a question here from
okay, yes.
Does the mass loss and energy produced in the PP reaction include the annihilation of the positrons produced? Yes, it does, because the positrons that are produced will annihilate with electrons, but that's a relatively small fraction of the energy that's generated.
Okay, thank you. Has anyone else got any questions?
Hi, Peter. It's Tony Hirsch here. I've got a question for you. It's a great talk, by the way. Thank you very much. But I've always been puzzled by the idea of shells of elements around the stars that are going to become supernova? Because, well, if there are shells of elements, I'd be interested to know how thick they are. But it's always seemed to me so unlikely that there's still nuclear fusion going on in the core. You'd think that all those shells of elements would be sort of mixed up together with being so close to a nuclear reaction. Why I know they're different weights, but
Yes.
why do they still settle out into shells of elements?
Right. The reason that they do that is it depends on the internal structure of a star. And so there are some parts of a star, and it's generally in the center, where there's no convection going on. The way that the heat distribution works is that it just forms stable strata, and that word doesn't actually make sense if it's all the same thing like hydrogen, but the gas just sits there. For certain stars, and this includes the sun, towards the outer parts of the sun, then in order to get the flow of heat moving through the star, then you do need to have convection. And if you've got convection, then it's just like boiling a pan of water. Everything would be mixed up and turbulent. But in the center, that's not what happens. And so I'm sure it's not quite as clear cut as it's always drawn, but broadly speaking, that will be the case because nothing's stirring it up.
Thank you, Tony. Thank you, Peter. Face, do you want to pick up? I see a couple of questions on my screen. Simon Pinnock, does the mass loss and energy produced in the PP reaction include annihilation of the positrons produced?
Right. Yes, I answered that one. Answer yes.
Forgive me.
Okay. Bryce says, how this knowledge is amazing. How does it help our day-to-day existence?
I think it helps in the sense that everyone really wants to know where they come from and what's going on out in the universe. There seems to be a basic human fascination. So if you ask the question, could we get by without this knowledge? Then the answer is clearly yes, we could. But if you ask, does it help to satisfy the human need for knowing what's going on and ultimately where we come from, then the answer is yes, it really helps answer that question.
Okay, actually this question's from Damien, not from me. Is the hydrogen nuclear reaction in the sun in any way similar to that in a hydrogen bomb or in the pursuit of nuclear energy?
It's very similar to the reaction in a hydrogen bomb, yes. So in a hydrogen bomb, then the temperatures are higher. So that means that the reactions will go a lot quicker. In the sun, the temperature is a mere 14 million degrees. And so if you were to follow one proton in its journey rattling around in the center of the sun, it would take several billion years for it actually to interact with another proton and so start this PP chain for that proton. And that's why the sun is very stable. It just sits there for billions of years. In a nuclear bomb, a hydrogen bomb, not the sort that were dropped on Japan back in the war, hydrogen bombs, then it is that sort of reaction, but the temperatures there are trillions of degrees, and so things just go very, very quickly.
Okay, you've got a couple more questions here. Before the neutron star merger discovery a few years ago, was it a major problem that the origin of a lot of the heavier elements was not fully understood?
In the sense that we didn't know that process, with hindsight, yes, it was. I'm not an expert in this area, but I believe people were not terribly fussed because it was thought that they were generated in supernova explosions. And then people looked at things in a bit more detail and thought, hang on, there's something that doesn't quite work out here. But that was theory not quite agreeing with observations in a way that you could sort of brush under the carpet for a bit. And then as the observations got firmer, people did come up with the idea of neutron star mergers, but we've never actually seen them, and now we have. So I think it's one of those things where, with hindsight, yeah, we got it wrong, but it wasn't obvious that we got it wrong earlier.
Yeah. Another question, is the distribution of elements throughout the universe the same, or do certain solar systems or galaxies have any differences?
If you look, but I'll talk about what I call the local universe. So many different galaxies, no, they are all the same in terms of the chemical elements and the distribution. If you look back to the earliest part of the universe that we can see, then the heavier elements, sorry, when I talk about heavy elements, I mean anything heavier than hydrogen, than helium, then the stars back then had less heavy elements because they hadn't been generated yet.
Okay.
So it's the age of the universe rather than the physical location in the universe, which is the important thing.
I had a question actually. You showed at the beginning all the elements in the body. Is the role and understood of all those elements?
I'm pretty sure it is, yes.
They're all essential to our everyday body workings.
And that's why they're there. That's why we've evolved that way.
Flab says, maybe a silly question, but why is the temperature not increasing in the sun?
Right. It is increasing very slowly. It's not increasing in the sense that, well, we're generating all this energy. Why doesn't that make it hotter? And the answer to that is because it leaks out. And the energy that leaks out is what we call sunlight. So there's a very delicate balance. Actually, it's not delicate, it's very stable. Essentially, what's generated in the center of the sun eventually makes its way out from the surface. I said that the neutrinos just shot out through everything and hardly interacted. So if you generate a neutrino in the center of the sun, 8.5 minutes later, we pick it up on the Earth, if we pick it up at all. If you generate one of those gamma rays, then it rattles around in the sun for about 500,000 years, bouncing off all sorts of things along the way, and eventually it comes out as optical light from the surface. And the fact that it takes such a long time is what gives a lot of stability. Having said that, as you're burning the hydrogen into helium, that does make very slow changes. And so over millions to billions of years, it is getting a bit hotter, but it's over that time scale.
Okay.
Okay.
I see you have another question from Tony, but can I squeeze another one in?
Yeah.
Peter, it's interested in your observations. You obviously talked quite a lot about helium. I'm fascinated by the fact there is a company based not far away who believes there is a potentially viable reserve of helium under the crust of, would you believe, Oxfordshire. They are, we're trying to help them at the moment to get an exploration license from the Oil and Gas Authority and BEIS because it's helium. They don't need to go to any great lengths of drilling and fracking and whatever. They just need to put a pinprick through the crust of Oxfordshire to see what's down there. Helium arrives in curious, mysterious ways.
Yes, indeed. And it's amazing the uses that we put helium to. So yeah, everyone knows about helium balloons, and if you breathe in things from a helium balloon, then your voice goes funny, and this is all very amusing. But helium, liquid helium, when you cool it down to really low temperatures, John well knows, then you can get superconducting materials, and such things are becoming increasingly important. For example, at CERN, all of the magnets there are superconducting magnets, and they have to be cooled down to really low temperatures, like a couple of degrees above absolute zero. And so there's huge industrial and scientific needs for helium. And we are concerned there's not enough to go around. So yeah, if we can find a source under Oxfordshire, that would be great.
Serendipity.
Mm.
Okay, you've got another question here from Tony Hirsch. I've heard asteroids are potential sources of mining for useful elements, but why do they seem to have lots of particular types of elements rather than all being the same mixture? Because supernova always make the same types of elements in the same ratio?
Different supernovae will make slightly different ratios, but broadly that statement's true, yes. Asteroids are solid bodies, and they haven't got a lot of gravity. So lighter elements that don't form solids will just drift away from the surfaces. So you will predominantly get heavier elements that form solid bodies in asteroids. Now, whether it's commercially viable to go and do that is a source of debate. I know people are talking about going and getting them. And they certainly will have preferences for certain elements, valuable ones, but it's awfully expensive to go and get them. So we'll see.
Okay, I think that brings us to the end of our questions, unless anyone's got a last minute one.
Don't see any
No, I think that's
hands up on the screen, but I think we've got quite a bit of winding down to do anyway, Faith, given this is the 50th talk in the series so far. Well done, everybody involved in that. Thank you, everybody involved in that. And roll on to the next 50. But I think we have been blessed tonight with an amazing talk, Peter. You used the word stuff at the beginning of the talk, and I think, ladies and gentlemen, Peter really does know stuff. And I love it when he uses or mentions things like, well, it's just standard nuclear physics. Ho, ho, ho. Absolutely brilliant, amazing. We're really very, very fortunate to have you in our midst and have such a talk, Peter. And I should have said at the start that by attending Wantage Cafe Scientifique tonight to hear Peter's talk, you have all saved a small fortune. Peter is in big demand as a speaker on luxury cruise ships, and I meant to set you forth at the start, thinking you were going on a luxury cruise tonight. So
yes.
so I hope you really have enjoyed the experience. I certainly did, and Peter, thank you very, very much indeed. Amazing.
Enjoyed it myself.
Thank you.
And we are wrapping up for Christmas tonight, and we restart in the new year. We haven't locked down the plans for the individual talks. The calendar, I think, is pretty well set, Faith. But we haven't matched up the talks, and we have a number of sorts in mind. We also just been having a think back over the talks that we have been fortunate to have in the last year and beyond. Faith, I don't know if you want to say anything about.
Well, we've had a huge variety of talks, even just in this last year. Sorry, I don't know if anyone has particular memories, but we've had quite a varied selection this year, ranging from organic farming and protection of the soil and bees to the latest COVID stories and the climate emergency and the science or art of advertising. So we've covered quite a broad breadth, I think, and we'd like to see that going forward to next year. So we're always open to suggestions. We can't always follow everyone's up, but yes, if anyone does have particular or knows any scientists or has particular topics they'd like us to see if we can get a speaker for, then please make the suggestion. And yeah, I think that's all really. I think we only realised recently we've been going for 50 sessions. John and I have only been involved in the last few years, and we took over from Mim, so it shows that 2 people were needed to do Mim's job. But so
Here, well done, Mim.
yeah, and yeah, so we hope we can carry it forward in the same way. But no, we don't know of the future of the beacon at the moment, and hope we'll be back there sometime next year. But for now, we'll be looking for more Zoom speakers, I think.
Brilliant. So we will Zoom back in the new year. But for now, huge thank you again to Faith for all the hard work she does. Amazing talk tonight, Peter. Thank you very, very much indeed. And thank you everybody for being such a great audience, great questions, and it seems a very vibrant Café Scientifique. So onwards and onwards and onwards. Have a fantastic Christmas, and here's to the next 50. All the very best.
Thank you.
Okay,
Thanks, Peter.
thank you.
You're welcome. I'm
Thanks,
parched
Peter.
there, so I shall go get myself a drink.
Yeah, good for you. Yes, you
Bye, everybody.
Thank you.
Thanks,
Bye.
thanks again,
Bye.
Peter. Thank you, John. Thank you, Faith.
Okay.